There we go.
All right. So let me continue from last time. Actually, just to make this point, I'm very glad about what Guy spoke about today, because a lot of the structures that he introduced, including the principal series representations, including this very nice structure for scattering amplitude, the 4-point scattering amplitudes, I was going to explain in my later lectures, but I no longer have to do that, so I can just use those results. So that saves me some time, which is great. But yeah, so keep that in mind. You'll see the principal series, discrete series, including this idea of these sort of Euclidean CFTs, which look non-unitary but are not really non-unitary. They show up in celestial CFTs a lot as well, which I'll come to in a later lecture. Okay, so just to remind you what we talked about yesterday. So yesterday I just did some standard QFT calculations in order to derive these two formulas that I've shown, that I've written up there on the board. The first one is the Soft Theorem, which tells us that if I have any n plus 1 point amplitude and I take a soft limit for the photon, I specifically derived it for the photon, but such soft theorems exist for gravitons and gluons, and then there are many other soft theorems with sub-leading soft limits as well, which are all universal. There's a very rich structure. But I specifically just focused on this one particular soft photon. We end up finding that there's a 1 over q pole, and that the factor corresponding to that pole is what's known as the Weinberg pole, and it's completely universal. It only depends on the charges and the momenta of the external particle, not on any interactions or any other details of the theory. The second thing we ran through, and this was a bit fast, but hopefully since it was just sort of standard type Feynman diagrammatic calculations, even if you didn't follow it completely, hopefully you should be able to reproduce it if you're ever interested in doing that. There we showed that if I actually have massless photons in my theory, then any n-point amplitude, they don't have to have external photons in the state. Any n-point amplitude always factorizes into two pieces. This first factor, which I call e to the minus a, and the second factor that's just the hard amplitude. And the point of separating these two things out was that A somehow captures the effects of all the soft virtual photons, so the off-shell photons that are soft. And in particular, we calculated the exact factor for this A, which looks like this nasty integral, which I'm going to manipulate not today, but in the next lecture. And in particular, we found that when D is infinity, A essentially becomes plus infinity, therefore telling us that e to the minus A is 0, implying that all S matrices in gauge theories are 0, which is obviously not true. So today what I'm going to do is I'm going to introduce the idea of asymptotic symmetries, and here I'm going to use the space-time picture. If you remember, I told you that yesterday that there are two sort of ways to approach celestial holography. First is to study it from space-time, and the other one is to study directly from S matrices. In today's lecture, I'm going to sort of study it from the space-time point of view, and you'll see the calculations depend strongly on dimension, and 4 dimensions is much easier, so I'll focus on that in the lecture, but it has been done in the literature. It has been done for greater than 4 dimensions as well, but the calculations are extremely tedious, so there's no point going through it in these short lectures. So in 4 dimensions, I'll use a space-time construction, derive what I define for you asymptotic symmetries, find the Ward identity for those asymptotic symmetries, and show that that exactly reproduces equation number 1. That's the goal for today's talk. Okay, so the tool I'm going to use for this is called the covariant phase space. Any questions? Okay, so the tool I'm going to use is covariant phase space. This formalism, or rather covariant phase space formalism, this formalism is really, really very general. It can be applied to any theory, gravitational or not, in any geometry, with or without boundaries. It doesn't matter. At least the idea on this tool in principle can be applied. Now, depending on which particular geometry you're going to apply it to, you'll get different interesting results. Okay. In essence, the idea of what this formalism does for you is something very simple. Is that given a Lagrangian, so the input for this formalism, you have to tell me the Lagrangian. That's the input. And from this input, I can construct for you the phase space and the symplectic form of the theory completely. Now you might say, I already know how to do that because that's the first thing you learn in QFT is how to do canonical quantization. Given L, you take a derivative with respect to phi dot to find pi, and then phi with pi, the bracket of phi with pi is I h bar. That's canonical quantization. In essence, what you have done is constructed the symplectic form. So you've already done that. Except that this arrow is very general. As I said, applies to any space-time. It applies to any Cauchy slice. So it doesn't have to be a constant time slice. In particular, the ones that we'll be interested in is Scri plus. So we want to apply this formalism to a null slice. And more, on top of that, it keeps very careful track of boundary contributions to the symplectic form, which in our discussion will be exceedingly important and something that is completely missed in any of the standard canonical quantization discussions that you may have seen. So that's why this formalism is extremely powerful.
Does it also apply to higher derivative theory?
Any theory, any Lagrangian, no matter how many derivatives, any background, any boundaries, whatever, it doesn't matter. The formalism is general. You can then apply it in specific cases as you wish. So let me first tell you what the formalism is. So before I can tell you what the formalism is, because maybe it may not be common knowledge, let me remind you what a phase space is. So phase space is a symplectic manifold. And I'm going to try and use notation to describe this phase space that's going to be useful in this. So a phase space is a symplectic manifold, commonly denoted by capital gamma. So in this phase space, every point over here is an on-shell field configuration. So some on-shell solution. So every different solution corresponds to a single point on this phase space. And then field variations, delta phi, which of course maps you from phi to a neighboring point phi plus delta phi. So you can think of field variations as a vector in the tangent space of gamma at this point. So in other words, you can think of field variations delta phi as an element of the tangent space of gamma at the point phi. Okay? So let me repeat that. Every given field configuration is a point on that surface, and then a variation, a linearized variation away from that point, by which I mean delta phi. Remember, everything is on shell, so delta phi therefore must satisfy the linearized equations of motion in the background of phi. So delta phi is a solution to the linearized equations of motion. So delta phi can be thought of as a vector field in this tangent space. Okay, it has basically one important structure, is that it contains a two form. There's a globally defined two form, and a two form, if you remember, is defined by two inputs, two vectors. So you should think of this, roughly speaking, think of this as omega AB, delta phi A. So remember, delta phi is a vector, so it has an upper index, and then omega has some lower indices, and it's a two form. It's antisymmetric in these two forms. This omega has two crucial properties, is that it's closed and it's non-degenerate. This means that's to say, if for instance omega AB is equal to 0, for any given delta phi, this must imply that delta phi A is 0. This is of course another way of saying that this omega is invertible as a matrix.
Sorry, is every point phi in non-total correspondence to the initial data on the Cauchy slice?
Yes, because that's how you define Cauchy data. There's a unique map.
Hyperbolic.
I haven't introduced space-time yet. I'm just talking about phase spaces. I'm going to do that. Covariant phase space. We'll assume that. Okay. So this first property tells us that, barring some topological issues, that omega can be written as d of theta.
So here you don't need the information about pi.
No. So I'm being very general in my notation. So you can think of q and p as generalized coordinates xa. So with this A index being this one on my phase space. So this A is an even dimensional variable. It captures both Q and P. Now, Q and P are specialized coordinates where where this omega takes a special off-diagonal form. But of course, as a manifold, you don't have to work in this basis. You can work in any basis of coordinate systems, and then I'm trying to keep it general.
What is XA?
Huh?
What is XA?
Oh, just delta phi A. What I meant, sorry. Roughly. So when you think of Q and P of phi and pi, phi dot, that's what you usually think of as a symplectic form, but I'm just using completely covariant notation. The whole point of covariant phase space is going to be completely covariant. Covariant on gamma, covariant on space-time. Everything is going to be in covariant notation.
And what is the difference between D and delta?
This D is an exterior derivative on gamma. So I don't know if you know these formulas, but in standard differential geometry, so for example, if I give you D of let's say a function, so D of a function is a 1 form, right? So as a 1 form, it takes a vector as an argument and returns a real number. So it should take a delta phi as an argument, and it should return for me another function. So and that function is roughly speaking delta phi as a vector field acting on the function f. So I'm just using sort of very covariant notation to describe everything. More perhaps d theta, let's look at theta so that you're familiar with this formula over here. Theta is a 1 form, so d gamma is now giving me a 2 form, so I should have 2 inputs, phi delta phi prime. And this in terms of theta is simply the statement that delta theta delta delta prime phi minus delta prime theta delta phi minus theta so that's what it means explicitly. But this just means exterior derivative on gamma. Yeah, good point. I'm going to eventually also talk about exterior derivatives in space-time, so it's important to keep track of this distinction. Okay, now here, this equality is sort of only true if H1 of gamma is 0. Is the empty set. It just says 0. This is a crucial assumption that we anyway have to make, because the Lagrangian doesn't exist unless theta exists. The existence of theta is closely related to the existence of the Lagrangian, and whenever theta doesn't exist, there's a standard theory in phase space, which all you have to do is you have to extend your phase space by introducing some auxiliary set of variables. And once you introduce some auxiliary set of variables on this extended phase space, you have a topologically trivial phase space, and you can then define such a 1 form. So for example, a really trivial example just in terms of geometry is that if I look at a disk as gamma, this is of course not topologically trivial, so this equality would not be true, but then I can just introduce extra dimensions by sort of extending it in this direction, and now if I have a loop over here, I can pull it up and then contract it down there. So by introducing these auxiliary variables, of course in a smart way, you can't just do whatever you want, you can always set this to be true. An example of this is, for example, the WZW action, which as you know is not gauge invariant unless you add the WZ term. And in order to add the WZ term, you have to introduce a third dimension with some auxiliary fields, just as an intermediate tool to define that quantity. And that's the same thing that's happening there. The phase space for WZW theories is not defined unless you introduce auxiliary variables. Okay, so in any case, I'm assuming you do all of that, and then theta is perfectly globally well defined. Yes?
So just a quick question. Does it mean that all of in the classic constraint, does this mean that all the non-trivial topologies and constraints are like 1-to-1 cross 1?
I'm not talking about space-time topologies. No. I don't know if there's a 1-to-1 constraint.
I mean the non-trivial topology in phase space, is that in 1-to-1 correspondence with constraints on your classical?
I don't know if it's a 1-to-1 correspondence, but there is a correspondence. I don't know if it's a 1-to-1 map. And then there's another thing that I'm going to come to. Maybe I don't know if I want to mention that. So this is about H2, which talks about omega over here. But of course, another important factor is H1. that defines for you whether theta is uniquely defined or not. And indeed it's possible, in the example that I showed, for example, it was actually about H1, and it might be possible that H1 is non-zero. And this is very important in the quantum theory, and this an famous example of this is the theta angle in QCD, which, and the topological, on the phase space point of view, which those theta angles show up here. But I'm going to ignore all those issues, and I'm going to set it to 0 for simplicity here. Okay. One last thing. The next thing about this is canonical transformation. So what are canonical transformations? Canonical transformations are diffeomorphisms on the phase space. These are phase space diffeomorphisms, not space-time diffeomorphisms, which preserve omega. So that's the definition of a canonical transformation, at least an infinitesimal canonical transformation. These such psis are often called Hamiltonian vector fields in this context. But there's a very nice property for the Lie derivative, which is always true. You can always write the Lie derivative as di psi. That's just, it's the Cartan homotopy formula. That's always true. But if omega is closed, then this second term vanishes. And so I just have d, this is 0, and because I'm assuming that h1 is 0, this means that I is always given by d of some function. And this function is the charge that generates, is the conserved quantity corresponding to this psi. This is called the Hamiltonian charge. Essentially what we'll be doing in our entire story is that the psi that we'll be choosing is gauge symmetries, and then we'll use this procedure to construct a charge that generates gauge symmetries. And we'll find that it's non-zero, implying that it's actually physical. And we'll then explain what that means. Okay?
You quotient out by the gauge symmetries to define your phase space.
I'll come to that. I will come to that. That's associated with this non-degeneracy property. Okay, that's all I have to say, and that's all I need to say about. Oh, maybe one more thing. This is a very interesting fact. Honestly, even I knew all of this for a long time, but I didn't appreciate this very simple fact. This is essentially telling us that there's a one-to-one map between functions and Hamiltonian vector fields. Of course, the inverse is true, because every time I have a function, I can just define my Hamiltonian vector field by this formula. But if h1 is 0, then it's indeed it's a one-to-one and invertible map. But interestingly, because suppose I have two Hamiltonian vector fields, psi1 and psi2. They're both Hamiltonian vector fields, so that the Lie derivative acting on omega is 0. That means the commutator of these Lie derivatives acting on omega is also 0, obviously. But the commutator of Lie derivatives is the Lie derivative of with respect to the commutator. So this is the Lie bracket. Consequently, because of this one-to-one map, if psi1 is a Hamiltonian vector field, psi2 is a Hamiltonian vector field, then commutator of psi1 and psi2 is also a Hamiltonian vector field. Therefore, if there is a Hamiltonian charge for this vector field, there must be a Hamiltonian charge for this vector and a Hamiltonian charge for this vector field. There must be a Hamiltonian charge for that vector field. It's the Poisson bracket. So the Hamiltonian charge is the Poisson bracket of. So this is why they say that these charges form an algebra, which is the same algebra as the algebra of these Hamiltonian vector fields itself. Okay. Okay, let's now start with, so far this was just a very brief review on phase space. Now let me tell you what we need to do in covariant phase space. So I'm just going to tell you the steps, and then we are going to go through a short example just to convince all of you that we end up with the exact answer that we expect in the constant time slice case, which you're all familiar with. So here are all the steps that you have to do. As I said, the input is going to be a Lagrangian, and in my notation I'm going to use as my Lagrangian is always going to be a D form. And the reason I'm using this distinction is I want to really write everything down in a notation that can be easily generalized also to gravity. Because otherwise there's a square root g, which you also have to vary in the case of gravity. But if you write everything in terms of forms, then everything that I'm going to say generalizes I don't have to change a single word or sentence to generalize it exactly to GR. So suppose I have a form. So this is a D form. Of course, because it's a D form, I can always write it as the epsilon tensor times the Lagrangian density, as we know, but I'm not going to do that here. And you should think of phi at the moment at least, because at the moment phi is some element on some field configuration space. It's a set of all allowed field configurations. These are usually fixed. For instance, you have to impose some boundary conditions to define f. So for example, in 4 dimensions, you might want to say that phi falls off like 1 over r at large R. I'm not imposing on shell conditions yet, but just some boundary conditions that define my field configuration space. Also note, in this L, I'm including any and all boundary terms that you may have to add to make the action well defined. This includes the Gibbons-Hawking term, this includes ADS counter terms, whatever you need to add to define your theory. The full action is given by this quantity right here.
So are they like D-1 forms, just take polyforms?
Yeah, you can always, as I said, you can always add dk to this, which is a D-1 form, and this k is the Gibbons-Hawking term. You could do that. And whatever that is, I'm including it in my definition of L. Okay, so this is given to us. So the first step is I'm going to vary L. This is the usual thing. So when you vary L, using the usual process, I get these two pieces. So usually, again, this is a general Lagrangian, so you can have many derivatives, infinitely many derivatives if it's higher spin type theories. You do the usual process. Every time you have a derivative acting on delta phi, you integrate by parts. But now we keep track of all the boundary terms. You do not throw away the boundary terms. We keep everything. So after you do this entire process, you remove every single derivative from delta phi, you get this piece, and everything else is necessarily a boundary term, which I absorb into a definition of this D-1 form. So you can immediately see the way to interpret this theta. This theta is a 1 form on f, because it takes as an input a field variation, which is a vector field, remember. So theta, vector field, and gives you a number out of it. So it's almost like the theta that I defined down here, except that is also a D-1 form in space-time, which of course, how do I get rid of? I integrate over a Cauchy slice, and that'll give me theta exactly, which is basically what I'll do in the next 2 steps. So this thing it has a very complicated name. I won't write it out. Symplectic potential current density. That's the name. Okay, given theta, define omega as the exterior derivative on f for theta. Again, you might see where I'm going with this. I want to define capital omega right here. So that's what I'm trying to do. So here it was an exterior derivative on gamma. I haven't yet defined gamma, what that is yet.
Can you repeat the name of this theta, sir?
Symplectic, let me write it down. It's symplectic potential current density.
I think there should be a pre before you take it.
No, I haven't said pre yet. I'm coming to that. I'm coming to that. There will be a pre. Sorry,
can you explain again that theta term how it appears?
You vary the action. You get delta phi terms, right? You'll find some terms in which the derivative is acting on delta phi. What do you do in order to derive equation? You integrate by parts every single time. But now you don't throw away the boundary terms. We keep all the boundary terms, and every single boundary term is absorbed into my definition of theta. Okay, so that's why it's a boundary term. It's a D. When I write D with no subscript, it's a D on space-time. It's a space-time exterior derivative.
How do you know it's of the form of some form acting on the vector field delta phi?
Because we know it's a boundary term. So boundary term will always be del mu theta mu. I can always write this as d of star theta. Always. Well, with an epsilon. So whatever this theta mu is, you take the, anyway, it's always possible to write it in form notation. Okay. Okay, now from now on, of course these are my Euler-Lagrange equations. So now I'm going to impose Euler-Lagrange equations. Just 1 minute. I'm going to impose Euler-Lagrange equations and work on a subspace of F, which is the solution space. So this is the subspace. Yeah.
Just about this question. So, how do you know that it's a function just of delta phi, not the field, or can it be?
No, it's not just a function of delta phi. It's of course a function because I'm varying around a point. So all of this is theta. You should think of as an element of the tangent space. So of course it has phi dependence, the point where you're doing the variation, and everything else. Okay, so now let's impose equations of motion everywhere. So now I'm sitting on an on-shell subspace of this. This is known as the solution space. Everything else I'm going to say is on the solution space. So now I'm going to do the obvious things. I'm going to define omega pre. This is the pre-symplectic form. And I'm going to define this as integral of omega over a Cauchy slice. Now this thing really is almost a symplectic form, because this omega was already a 2 form on F, so it already contains two delta prime inputs. The only problem was that it was a d minus 1 form, but when I integrate over this space-time, all of that stuff goes away, and so now on this side I really do have something that is a 2 form. I mean, it is a 2 form. It's antisymmetric in delta and delta prime, and you've given 2 inputs of vectors, it just gives you a real number, which is by definition a 2 form. Okay, what's stopping it from being a symplectic form is that we haven't checked that it's non-degenerate. It's exact by construction because it was obtained as an exterior derivative of theta. So obviously it is definitely exact, but we don't know if it's non-degenerate. So this is now very easy to fix. So the next thing we do, and in fact in gauge theories it will always be non-degenerate, and that's the part where gauge fixing comes into play, and we'll have to gauge fix in order to make the phase space well defined. So finally we define the phase space as the solution space modded out by the kernel of omega pre. So this is really simple. Every time omega has a null vector, you just map that to 0 and then mod out in the solution space, and this modding out feature will give you what we call the phase space, and then omega on this phase space is defined as you start with omega pre and then just induce it down to gamma, or gamma is simply defined by this. Okay, so looks like in the interest of time, I will not go through the example that I was planning to go through. I was planning to just do it for a scalar field and just show you that it gives us all the expected answers. I'll straight away now start and apply this to gauge theories and see where we go from there. Okay, questions? So I'm just going to now take gauge theory and apply 1, 2, 3, 4 and see where we go.
So it's a statement that at least in the standard theories that we work with all the time, this quotienting is also something smooth.
I don't know. I don't know the answer to that.
I think you assume that the kernel would be some distribution.
Yeah.
Just another question. So, like we normally integrate this like small omega on some Cauchy slice or some null hypothesis. What if we integrate on a timeless? What's the interpretation?
So there is a good reason to integrate it over Cauchy slices. Notice, maybe I should have mentioned this. Notice that I wrote sigma over here, but I didn't write sigma over there. In fact, this integral doesn't depend on the choice of sigma because sigma is a Cauchy slice. This is where the fact that it's a Cauchy slice becomes important. Of course, we want the phase space to not change as you just change, it just flow over time. You don't want to change the manifold. You can trace a path over the symplectic form. The symplectic form, in other words, another way to say this is that we would like time evolution, at least in flat space times, to be a symmetry, to be a symplectomorphism. So we don't want it to change omega.
Is it clear that you're assuming global hyperbolism?
Yes, of course, I'm assuming existence of Cauchy slice. However, as I said, everything I've said over here can be applied to any spacetime in any Cauchy slice. So in principle, I don't need to apply this formalism to a bulk Cauchy slice. I can apply it to an asymptotic Cauchy slice, and I don't care what's happening in the deep bulk. So for example, in flat spacetime, I'm going to apply this formalism to Scri plus. All I need is the existence of Scri plus, which is one of the definitions of asymptotically flat spacetimes. And then what's happening in the bulk, whether there's a black hole, which is evaporating, blah, 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 I don't care. It doesn't care. Okay. Let's do gauge theories, and I'm going to do free Maxwell gauge theory. Again, something you might think that you have studied quite a lot, but you will see when we keep track of boundary terms, I hope you will learn something new, even just for free Maxwell theories. Okay, so the Lagrangian under consideration is -1 over 2 e squared f wedge star f.
Perhaps just a clarification, because at the beginning you said that in L you include all possible boundary terms. So I mean there was a question about the Gibbon-Solving term, and you said you include in L. But if you include the Gibbon-Solving term in L, and you take the standard Dirichlet boundary conditions, then you do not get d theta, right? Because the Gibbon-Solving term is the term that, under variation, of the action, gives you exactly the equation of motion when you impose delta s equal to 0.
Yeah. So of course we have to assume. We have to
neglect the boundary terms if you want to have theta, and then read them from theta, right?
Not exactly neglect. We want to, when you do the variational principle, imposing Dirichlet boundary conditions, we have to ensure that theta vanishes when you impose Dirichlet boundary conditions. That's what I mean when I say add all the, maybe I shouldn't have said all possible, I should have said all the required boundary terms for the variational principle to make sense. Which means that theta should vanish under whatever choice of boundary conditions you're choosing to quantize your theory. Typically Dirichlet, but maybe Neumann, whatever you want. Theta has to vanish. Okay, of course with f is equal to dA. Okay, let's follow through the process. Step number 1, vary the action. So when I vary this action, what do I get? I get so I see that there's a derivative acting on A, so I integrate by parts in the usual way. So I'm going to get -1 over e squared and then I get minus okay. So I'm going to read this off as theta. Using same notation, theta, small theta. One, maybe, I don't know if you guys have thought about this, it's not immediately obvious that you can extract theta uniquely from this boundary term, because of course in principle I can take this and add something that looks like d of y completely, and it won't change the variation of the action. So in fact theta is only defined up to such boundary terms, and this will affect the symplectic form later on, but I'm going to ignore it for now. I'm going to just do the simplest possible case. In fact, such y terms are needed when you have Chern-Simons theories. The theta angles, which gives you the Chern-Simons action here, this y. But I'm going to ignore this issue. Okay, so this is theta. So let me just basically do 2 steps number 2 plus 3 in one go. And omega pre is you integrate over a Cauchy slice of Okay, so clearly it's almost a symplectic form, it's anti-symmetric in delta and delta prime, and if you give me some set of variations, delta A and delta F, delta A and delta prime A, I can just plug it into this equation, integrate this over whatever Cauchy slice I want, and I'm going to get a number. Okay, but this is non-degenerate. How do I see that? So in order to check that it's non-degenerate, what do I need to do? Well, in principle, I need to classify all the null vectors of this omega. And I'm not going to prove to you that these are all of them. I'm just going to show you one of them, the most important one. And in fact, that's all of them, at least in this case of the free Maxwell theory. So here's a simple vector field. Remember, vector field are field variation. So I need to tell you a particular field variation, which is, as you may guess, is going to be a gauge transformation. Consider this field variation. Remember, I'm on shell. Right, so when I'm on shell, d star f is 0 because of equations of motion is coming in from there. And of course, even the variations are on shell. That's what I mean, everything is on shell. So we also have d star delta f is 0. Okay, so let's plug this in over here. So if I plug it in omega pre delta, so delta lambda. Let me just sort of run through what I would get. So when delta A, so delta lambda, so I need to take the delta prime and plug it in. So delta prime of f, when it's a gauge transformation, is 0 because f is gauge invariant. So this term doesn't contribute at all. This term gives me d of lambda, but I can integrate by parts. When I integrate by parts, I get one term in which this d acts on this delta f, but that's 0 because of equations of motion. So the only term that survives is the boundary term, is the total derivative term. So what I get at the end of the day is 1 over e squared integral over the boundary of the Cauchy slice of lambda star f, lambda star delta f. Yeah. Okay. Now you may immediately see what's going on, and this is the first signature of asymptotic symmetries. If lambda on the boundary of sigma is 0, so lambda is a gauge transformation, it's defined everywhere on the Cauchy slice. If it vanishes on the boundary, then the right hand side is equal to 0 because this is just an integral over the boundary. I don't care what it's doing inside. So then we see that delta lambda is an element of the kernel. Therefore, in order to construct the phase space in step number 4, what do we need to do? We need to identify all solutions which are related to each other by small gauge transformations. So by small, the specific, what I mean is if it vanishes on del sigma. So just to be emphasize this even more, it is not true that all solutions which are related by gauge transformations are equivalent. They have to be related by small gauge transformations. There's a crucial distinction that I want to make. Of course, let's say, on the other hand, so that's it. So by the way, this is the only null vector in this particular case. So let's assume that I've done this, I've modded it out, and I've constructed the phase space. Now I have my phase space. Now let's talk about canonical transformations. But I can already read off a canonical transformation right away from here. Now if I consider the case where this does not vanish on the boundary of del sigma. And in addition, I assume that delta lambda is equal to 0. What does this mean? I assume that lambda does not depend on the fields itself. And again, I don't even really need it to be 0 everywhere. I just need it to be 0 on the boundary. You might think this is technical, but it's not really, because depending on which gauge you choose to work in, because you have to choose a gauge now that I have to mod out, the set of residual gauge transformations might actually end up depending on the background metric. So you have to be a bit careful to figure out whether this is actually true. In the gauge theory case, it turns out to always be true. But when we talk about BMS transformations, then you will find that the diffeomorphism that generates the BMS group depends on the background geometry as well. In that case, it turns out that delta of the diffeomorphism is not equal to 0, but delta of the diffeomorphism on the boundary is equal to 0, which therefore still continues to make it a...
Is it delta or delta lambda?
No, I'm taking the field variation. So here I just assume lambda is any function, But this lambda could itself depend on A. In principle, it's an arbitrary function. It could be anything. And I'm now assuming this is the assumption that lambda does not have any field dependence. So in other words, on the phase space, it's a constant. It's not a constant in space time, but it's a constant on the phase space. That's what this is. This is that assumption.
But it's only a constant
Not in space time.
on the phase space when you take the phase space to the boundary of the Cauchy slice.
No, I haven't taken any. This is the full Cauchy slice. The phase space is not on. Phase space is a separate space time, unrelated to the space time that I'm working in. Okay, suppose I do these two things, then what do I get? Then I find that omega. Now I'm dropping the pre symbol because I've assumed you've sort of modded out by these things over here. We find that delta lambda is equal to delta is the total derivative. Now I can pull this delta all the way out, and I get 1 over e squared integral of lambda star f. But this is precisely the definition of canonical transformations. This was gamma. I should have kept all of these gammas everywhere. All of this is on gamma. This is the definition of I sigma is what? I sigma is you just contract, one of the indices of omega is contracted with whatever transformation you're looking at, in this case large gauge transformations. And then the claim is that the result for any vector field is just that it should be a total variation of some function inside. And that function is the Hamiltonian charge for this, which we call the large gauge charge.
But the variation is not in a phase space, right?
This is a delta on phase space. It's a vector field on phase space.
And that's the same as the
It's the same as that. This formula, let's parse this out a little bit. This, in index notation, this formula is a statement that omega AB psi b is equal to del A H psi, right? Let's contract this with an arbitrary phi on both sides. This is the state, this is omega delta psi, that's this left hand side, and this is delta of H psi. It's the action of the vector field on the function, which is exactly what I have here if I think of psi as delta lambda. This is exactly this formula here. Okay, let me summarize. In gauge theories, now let me just say something. What I did over here was for free theories, but really just for simplicity. This is true generally in any gauge theory. In any gauge theory with any Lagrangian, with any higher derivative terms, whatever you want to write, small gauge transformations are always redundancies. And in order to define the phase space, you have to mod them out, choose a gauge, do whatever, one of those things. Large gauge transformations are not they are not redundancies. They are physical. They have non-zero charges on the phase space. They are always canonical transformations, and their charge is always given by the integral of lambda times star f evaluated on the boundary. Okay.
In what sense is a canonical transformation physical?
A canonical transformation is the thing that generates symmetries. All symmetries are canonical transformations. In fact, that's all canonical transformations are symmetries. Some symmetries are not always canonical transformations, and that depends on your boundary conditions. You have to impose boundary conditions to make them symmetries. Well, given the time, now that you mention it, let me just say this right here. This is I think a cool result that is not appreciated. What's another canonical transformation? Rather, let's start with saying, what's another symmetry that you believe is always a symmetry of QFT, any QFT? Let's say in flat space-time. Poincare symmetry. We expect we expect them to be symmetries, obviously. Or more generally, if I do it in any other background, the isometry group of that background. Here's what I find if I do this entire analysis, but now for isometries. you'll end up finding that omega delta psi is, now this psi is a diffeomorphism that generates that whatever isometry that is. In flat space-time, it will be the Poincare group. In ADS, it will be the CFT group minus integral over the boundary of something that looks like. Right away, we notice that it's not a canonical transformation. Because it's not a total variation, there's this extra term. So the first step in order to make it canonical is that we have to ensure that we have the right boundary conditions to get rid of this second term. Usually we do that in field theory by assuming that everything falls off on the boundary. That will obviously get rid of this term, but as we'll see, assuming that everything falls off, especially in gauge series, will be a big problem. So we can't assume that everything falls off, so we have to be very careful in making sure this term is 0, but not identically 0. Like it's 0 after imposing some funny boundary conditions. But even more than that, if I now write down what is H sigma, it's probably exactly what you expect. It's the integral over sigma So of course that's just this is exactly what we expect the Hamiltonian charge to be. You take the stress tensor, contract it with whatever isometry field you have, and then integrate. However, you have extra terms. And especially in gauge theories, you have where this quantity is what I'm calling Q lambda. It's the large gauge charge. The large gauge charge shows up in the charge for isometries. So two things. You have this extra boundary term, which shows up only if your theory has higher derivative terms in it. So in the case of the free abelian theory, free Maxwell theory, this is just identically 0. It receives only contributions from higher derivative terms. This stress tensor, by the way, is the GR stress tensor, the symmetric one. So then you have this boundary term, and then you have an extra boundary term corresponding to these large gauge charges. And in fact, this will be the consequence of the fact that we'll see at the end of the day that in gauge theories, you have an infinite dimensional vacuum Hilbert space. You have infinitely many vacuum states, which immediately violates the first assumption we make in QFT, that the vacuum is unique. But more than that, we'll find, because of this term, in the isometry charge, it's not even Lorentz invariant. So not only is the vacuum not unique, you have infinitely many vacuum states, and almost all of them are not Lorentz invariant. There is one vacuum state which is Lorentz invariant, and that is the vacuum state that you usually compute Feynman diagrams in. But there's also infinitely many other vacuum states which you don't usually study in QFT, and the existence of those, the fact that those vacuum states exist and the fact that we ignore them is associated with the fact that scattering amplitudes work out to be 0, because we are not keeping track of vacuum to vacuum transitions.
Notice that the vacuum states if they're not invariant in the symmetry.
They're vacuum states because they have 0 energy. Hamiltonian acting on them is 0. Okay, so let me just see. How much time do I have? 5 minutes?
Yeah.
I started a bit late. Okay, so again, all of this was totally general. Any dimension, any geometry, you can apply it to anything. Now I'm going to do the thing that I'm really interested in, is I'm going to apply it to flat spacetimes, Minkowski spacetime, on Scri plus. Okay, so we'll see that the fact that we are applying it to a null slice is going to give us some fascinating features. And well, clearly I won't be able to do it today, but I'll continue whenever my next lecture is in order to derive that person. So what I'm going to simply do today in order to set up the calculation is introduce the right set of coordinates to work in to do the calculation. Okay, so let me start with coordinates that I'm sure you're familiar with. Okay, the standard spherical coordinates. Should I? Well, okay, this I can still make a d-dimensional discussion. This is always true. Tomorrow I'm going to focus on 4 dimensions. Okay, so usually what one does in order to describe Scri plus, the standard coordinate system that one uses is that you define u is equal to t minus r, and in these coordinates Scri plus is defined as r goes to infinity, keeping u and theta fixed, where theta are the angles on this SD. So this is in order to define Scri plus, but we are going to be doing S matrices, so I need to talk about Scri plus and Scri minus. So I need Scri minus, v is t plus r. So you introduce a different coordinate system on Scri plus, for Scri minus. Okay, and when we do this, essentially the induced metric, of course Scri plus is an asymptotic boundary, so the metric on it is going to be divergent, but after you remove a divergent Weil factor, which is how you deal with conformal boundaries, the induced metric on both Scri plus and Scri minus is simply the metric of the sphere. That's just coming from this fact. Essentially, this divergent Weil factor is this r piece, so I just get rescale it out. This part is 0 because I'm sort of keeping r fixed when I'm taking the limit, and this part falls off because it's a 1 over r squared. Anyway, this is the induced conformal metric on it. And a second thing, I'm introducing these only because it's familiar, because now I'm going to tell you that these are bad coordinates, and I'm going to define a better set of coordinates for you. Another thing that we need, so this is fact number 1, fact number 2. A thing that will really show up now in detail is this antipodal matching condition will show up. As I've been trying to tell you that we want to keep track of the fact that Scri plus minus and Scri minus plus are distinct spheres. One of the things that we'll have to do in our discussion is impose what's called an antipodal matching condition. So this is a matching condition which takes a function which is a function on Scri plus minus. So it's a function on Scri plus minus, so it depends on some theta. And I'm going to equate it. This is what I'm calling a matching condition. To the analogous function on Scri minus plus, but evaluated at the antipodal point, not at the same point. So in other words, this is saying that I have a function on Scri plus and a function on Scri minus, and the matching condition tell me that the value of the function on the north pole is equal to the value of this other function on the south pole. So this is the antipodal matching condition. So I claim that these 3 features are bad. They are bad in what sense? Firstly, there's no way to describe Scri plus and Scri minus in a single set of coordinates. I have to change coordinates to go from one to the other. The metric on Scri plus in these coordinates is the round metric. Not that big of a deal, but you have to now deal with Christoffel symbols. Covariant derivatives are they're covariant derivatives, curvature tensors, and you have to deal with those things. Again, not that hard, but why put an extra confusions? And then the other thing is we have to do this antipodal matching condition, where the argument here theta, and you have to do some antipodal mapping here. And the antipodal mapping sometimes is very complicated depending on what coordinate system I'm using on the sphere. Okay, I can resolve all these 3 issues by defining a new coordinate system, and that's the one I'm going to be using. Yeah.
Out of curiosity, this F is going to be some field in some case.
Some field. So for example, it's going to be the radial electric field.
So if this is a complex scalar field, then do you complex conjugate one of the sides?
No.
It is just
It's a complex matching condition. Now, you don't. I haven't. No, you don't, I think. You don't.
something like that occurs implicitly. Never mind.
You don't. Okay, so the coordinate system I'm going to work with is, I don't know if it's called this, but this is the name I gave it in whatever paper I wrote, so, and no one has checked me on it, so I'm going to keep calling it this. Flat null coordinates. So here you take Cartesian coordinates, x mu, and you write it in these. So this r is not the same as this r. That's the spherical radius r. and you write it as, I mean, this is coming from ADS. They're not really new set of coordinates that much. And the metric looks very simple in these coordinates. That's the metric of Minkowski space. So, point number 1, scri plus minus is at r goes to plus minus infinity, keeping u and x prime fixed. Single coordinate system describes both geometries, both boundaries in one go. The induced conformal metric on scri plus is flat. Only partial derivatives will show up. So it's a very nice, and the matching condition in these coordinates is just the same argument on both sides. It turns out in these coordinates that this coordinate x, if it labels the north pole on scri plus, then on the south pole, that same if x equal to 0 is the north pole on scri plus, then x equal to 0 is the south pole on scri minus. So the coordinate just instead, like in other words, if I draw the map, the Penrose diagram, and include an angular term over here, the fixed angle mapping was essentially keepable. The fixed angle mapping was sitting at this fixed angle, but these x coordinates do something funny. They start off at here, and they move in some funny way like this, and they end up on there. So that by the time I reach scri minus, keeping x fixed, I automatically end up at the antipodal point on the sphere. So that's why I like these coordinates quite a lot. We can describe all of it in one go, and we don't have any complicated, funny antipodal matching condition. Okay, so that's all. I'm going to stop here, and next time I'm going to start doing actual calculations in these coordinates. Thank you.